In this work, we present CNS-Bench, a framework for benchmarking image classifier robustness under continuous nuisance shifts. Evaluating the robustness of vision models in out-of-distribution scenarios is crucial when they are deployed in real-world environments. Various works have shown that model performance drops in out-of-distribution scenarios, for example, for objects with a different texture or in different weather environments. Such performance drops differ for different distribution shifts. However, collecting real-world examples for all relevant distribution shifts is expensive. Therefore, various works have been proposed for synthetic benchmarking. For example, ImageNet-C proposes synthetic corruptions at multiple severity levels. Rendering pipelines enable very controlled distribution shifts, but implementing a new distribution shift requires large efforts. More recently, models have been evaluated with generated images. However, previous works only consider binary distribution shifts where the shift is either present or not. Our work closes this gap of generative benchmarking. Our framework CNS-Bench enables realistic, scalable, and continuous distribution shifts. This allows a more systematic robustness analysis and a more accurate estimate of the shift scale at which classifiers fail. The benchmarking images are generated using stable diffusion. To enable fine granular and continuous nuisance shifts, we train ImageNet-specific LoRA adapters that capture distribution shifts that are specified via text. During inference, increasing the weight of the LoRA adapter increases the effect of such a distribution shift. When performing a stronger distribution shift by increasing the weight of the LoRA adapter, the generated image might not correspond to the correct class anymore. Previous works mainly relied on a text alignment measure to filter out such samples. In contrast, we propose an ensemble filter that considers not only text alignment but also the alignment of the foundational features with respect to the original image. The thresholds are calibrated on a manually curated dataset. Our approach achieves a higher filter accuracy than the previous clip-based strategy. Finally, the CNS-Bench dataset consists of 14 diverse shifts and 6 nuisance shift levels. After filtering failed-generated images, 200,000 images remain that are used for evaluating image classifiers. Our analysis shows that the accuracy drops for increasing scales change differently for different shifts. For example, while the classifier performance increases gradually for the snow shift, the accuracy drops are sharper for the cartoon style shift. For some shifts, model rankings change with varying scales, as we can see for the painting style shift. We also introduced the failure point concept, which quantifies when models start failing for a given distribution shift. Such failure point distributions can vary between models, as we show in this example. Finally, we also evaluate the robustness of more than 40 classifiers and study their robustness on our proposed dataset along 3 axes: the model architecture, the model size, and pre-training strategies. We find that VMAMBA is more robust, that larger models typically correspond to a better model performance, and that pre-training with an SSL objective increases the robustness of a classifier. Let us conclude. In our work, we employed LoRA sliders to enable the evaluation of classifiers for realistic and continuous nuisance shifts and present a new dataset for benchmarking image classifiers. Our large-scale analysis supports that generative benchmarking enables new ways for evaluating vision models systematically. Thank you for watching this video.